Hi students, today's discussion is about chemical bonding. Okay, so chemical compounds are divided into two broad classes called ionic compounds and molecular compounds. Ionic and molecular compounds can be distinguished from each other on the basis of general physical properties. Ionic compounds tend to have high melting points, so around 500 degrees Celsius to 2000 degrees Celsius. And they are good conductors of electricity when they are in a molten or liquid state or in a solution. So in the succeeding lessons, we will know why they have this kind of properties. Molecular compounds, on the other hand, generally have a much lower melting points and tend to be gases, liquids, or low melting points solids, and they do not conduct electricity in the molten state or in their liquid state or in a solution. Ionic compounds, unlike molecular compounds, do not have molecules as their basic structural unit. Instead, an extended array of positively and negatively charged particles called ions is present. Some combinations of elements produce ionic compounds, whereas some would produce molecular compounds. But what determines whether the interaction of two elements produces ions or molecules is that the type is the type of chemical bond or chemical bonds present between or among the elements. So a chemical bond, this is the attractive force that holds two atoms together in a more complex unit. And chemical bonds, they are formed as a result of interactions between electrons found in the combining atoms. So the nature of chemical bonds is closely linked to electron configurations, which I suppose you have already learned, but later on we will have examples of this one. Corresponding to the two broad categories of chemical bonds or two types of chemical attractive forces, or we also call this one as chemical bonds. So we have ionic bond, and we also have covalent bond. So ionic bond is a chemical bond that is formed through the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. So we will have examples of this one later. As its name suggests, the ionic bond model, which is electron transfer, is used in describing the attractive forces in ionic compounds. So an ionic compound, therefore, is a compound in which ionic bonds are present. Okay? A covalent bond, on the other hand, is a chemical bond that is formed through the sharing of one or more pairs of electrons between the atoms or between two atoms. The covalent bond model, or electron sharing in this case, is used in describing the attractions between atoms in molecular compound. So a molecular compound is a compound in which covalent bonds are present. Okay, again, when we say ionic compound, this is a compound in which ionic bonds are present, while molecular compound is a compound in which covalent bonds are present. So in ionic bond, there is transfer of electrons, while in covalent bond, there is sharing of electrons. Okay. Okay, so you might wonder, or you might be asking why atoms would share or would transfer electrons and form chemical bonds. So one of the reasons of this is that they would want to achieve the kind of stability, or yes, the kind of stability that the noble gases are enjoying. That is why uh, they transfer and or they share their electrons. So in transferring, there is stability, in sharing as well. Okay. So even before considering the details of these two bond models, electron sharing and electron transfer, it is important to emphasize that the concepts of ionic and covalent bonds are actually quote-unquote convenience concepts, meaning uh, convenience, I mean, in a way that most bonds are not 100% ionic or 100% covalent. Instead, most bonds have some degree of both ionic and covalent character. That is, some degree of both the transfer and the sharing of electrons. However, it is easy, or it is easiest probably to understand these intermediate bonds, or the real bonds, by relating them to the pure or ideal bond types called ionic and covalent. So at this point in time, let us just settle on these concepts. There are two fundamental concepts, or two concepts that are considered important to understanding both the ionic and the covalent bonding models. One is that not all electrons in an atom participate in bonding. So those that participate, they are called valence electrons. I'd like to assume that you have already encountered this one in your high school chemistry. Another is that certain arrangements of the electrons are more stable than others, as is explained by the octet rule. So please recall that a valence electron is an electron in the outermost electron shell of a representative element or a noble gas element. So this applies only to representative elements and noble gas elements, okay? And a Lewis symbol is the chemical symbol of an element surrounded by dots equal in number to the number of valence electrons present in atoms of the element, like this one. So in the case of lithium, so lithium has one valence electron, so that is why it has one dot here. So for potassium, that's the same. And for boron, it has 3. For carbon, that's 4, so on and so forth. Okay. Okay, so let's try to look at the first concept in which not all electrons in an atom participate in bonding. So those that do are called valence electrons. So there are certain electrons which are called valence electrons, that are particularly important in determining the bonding characteristics of a given atom. So a valence electron is an electron in the outermost electron shell of a representative element or a noble gas element. That was mentioned earlier. But we have to take note of the restriction in this definition because it applies only to representative elements and noble gas elements. For such elements, valence electrons are always found in either S or P subshells. Okay, more complicated valence electron definitions for the transition and inner transition elements will not be considered for this lesson. And the presence of incompletely filled or F subshells is also or will not also be discussed further from this lesson. Maybe I will prepare also another or a separate discussion on that. So the number of valence electrons in an atom of a representative element can be determined from the atom's electron configuration. So later on, from I have prepared for this lesson some examples that would help us recall electron configuration, because through the electron configuration we would be able to determine the number of valence electrons. Okay, so another or the second important concept is that there are certain arrangements of electrons that are more stable than others, as is explained by the octet rule. In fact, scientists have developed a shorthand system for designating the number of valence electrons present in atoms of an element. And this system involves the use of Lewis symbols. A Lewis symbol is the chemical symbol of an element surrounded by dots, wherein the dots here would be equal to the number of valence electrons present in the atoms of the element. Okay, so this figure here gives the Lewis symbols for the first 20 elements, and the Lewis symbols are also frequently called electron dot structures. So they are named in honor of the American chemist Gilbert Newton Lewis. Okay. Okay, so let's try this one. Let's determine the number of valence electrons in atoms of each of the following elements. So if we have magnesium, silicon, and arsenic, let's try first magnesium. So the 12 here represents the atomic number, because this one is the subscript. If it is a superscript, so it should be the mass number. But in this case, 12 here is the atomic number. So the atomic number from our previous lessons is equal to the number of protons, which is also equal to the number of electrons. So remember or take note that we will go over the electron configuration in order for us to determine the number of valence electrons. Okay, so for magnesium, uh, the electron configuration would be 1s2, 2s2, 2p6, and 3s2. So the highest value of the electron shell number here is 3. So the number of electrons in the highest value of the electron shell would be equal to the valence electrons. So for magnesium, we have 2 electrons. Okay. Okay, how about for silicon? So silicon here has 14 protons, which is also equal to 14 electrons. So since this is an atom, um, the electron configuration would be 1s2, 2s2, 2p6, 3s2, and 3p2. Okay, so take note that electrons in two different subshells can simultaneously be valence electrons. So the highest shell number here is 3, and both the 3s and 3p subshells belong to this shell. Okay, so hence all the electrons in both of these subshells are valence electrons. So in this case, silicon would have 2 plus 2. So silicon would have 4 as the number of, or 4 as valence electrons. Okay. Okay, so for arsenic, arsenic has 33 protons, which is also equal to 33 electrons, and its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. Now, the highest value of the electron shell would be 4. So shell 4 is the outermost shell and has the maximum N value. Okay, the 3D subshell is in shell 3, so this is not counted, or the electrons here are not counted as valence electrons. Okay, in this case, we only have 2 and 3 for shell 4, so we have 5 as the valence electrons, or the valence electrons for arsenic would be equal to 5. Okay. Okay, so the general practice in writing Lewis symbols is to place the first 4 dots separately on the 4 sides of the chemical symbol, and then begin pairing the dots as further dots are added. And please take note that it makes no difference on which side of the symbol the process of adding dots begin. Okay, so we have the following notations for the Lewis symbol, which are or which could be summarized in 3 important generalizations about the valence electrons. One is that representative elements in the same group of the periodic table have the same number of valence electrons. So this should not be surprising, because elements in the same group in the periodic table have similar chemical properties, so as a result of their similar outer shell electron configurations. Okay, so the electrons in the outermost shell are the valence electrons. Next is that the number of valence electrons for representative elements is the same as the Roman numeral periodic table group number. Okay, so example for this would be the Lewis symbols for oxygen and sulfur. Oxygen and sulfur are both members of group 6A, so they have 6 dots. Similarly, the Lewis symbols for hydrogen, lithium, sodium, and potassium, which are all members of group 1A, so they have 1 dot. Okay, so the maximum number of valence electrons for any element is 8. Okay, so only the noble gases beginning with neon have the maximum number of 8 electrons. Of course, helium only has 2, and this is considered an exception in the noble gas family. Okay, obviously also an element with a total of 2 electrons cannot have 8 valence electrons, although electron shells with n greater than 2 are capable of holding more than 8 electrons, so they do so only when they are no longer the outermost shell and thus are not the valence electrons. So for example, earlier in the case of arsenic, it has 18 electrons in its third shell. However, shell 4 is the N shell, and I mean the highest N shell, and it has the valence shell or valence electrons for arsenic. Okay, so so let's have an example, or let's have examples so we could understand better the previous slide. So in this case, we are to write the Lewis symbols for oxygen, sulfur, and selenium. So these 3 elements are all group 6A elements and thus possess 6 valence electrons. So the number of valence electrons and the periodic table group number will always match 4 representative elements. So let's have oxygen, sulfur, and selenium. So first, let's try to put the dots at each corner of the chemical symbol. Then since they would have 6 electrons, so start pairing. So in this case, oxygen would be needing 2 more electrons to become or to achieve stability. Okay. The same is true with sulfur and selenium. Okay. Okay. How about this one for boron, carbon, and nitrogen? So boron is in group 3A, meaning to say it will have 3 electrons. And for carbon, it's in 4A, so 4 electrons. And for nitrogen, so 5A. Okay, so it would have 5 electrons. Okay. Okay, so that ends our lesson. Thank you.